The object or system in this experiment will be a wiffle ball. Okay, lab 2, the motion of a falling object. The system was our wiffle ball with a mass of 2/100ths of a kilogram and a radius of 7/10ths of a meter. We dropped the ball a distance of 2 meters, measured along the negative y-axis. We measured along the length of a wall 1 meter from tape to tape and from tape to floor. We set up our origin at the point of release. We rotated our axis -1 degree, and we can track it. We can see as it drops, it kind of waves right here. It has another little wave right there, and then it has another couple little waves as it drops down. But this is a wiffle ball, so the whole point was to drop an object that was going to have some drag resistance. We can see from the results that it dropped and it traveled about 2 meters in about 0.667 seconds. Okay, so we can see that. Let's turn off our axis. Let's turn off our calibration. Let's just watch it for a second. So we can see as it drops, it's gaining momentum, it's gaining velocity. As it drops here, it starts off slower, and the farther it drops, the more acceleration it has. The more acceleration also increases the drag force. At a certain point, the drag force pushing up is going to equal the speed and the velocity of the gravity pulling it to the earth, which would be terminal velocity. We made some changes and entered in some of the variables to the starter code. We had we entered the ball's mass. We entered the time. We entered the average velocity. We kept F net 0, and we ran the equation. We ran the formula, and we got a ball that fell with constant velocity. And so then for round 2, we wanted to do a second experiment. For the second experiment, we added the weight force, which was the ball's mass times little g in the negative y direction. We also added the force drag, which is the drag coefficient times the ball's velocity. We also added the force net, which is the weight and the force drag. We also added arrow scales, which allowed us to see and visualize the velocity of the falling object. When we look at our data and we graph the data on a graph, we can see that the predicted motion was very close to the observed motion. The observed motion had about 20 plots. The predicted motion had many, many more. You can see it aligns up, but as it gets closer to the end of the elapsed time, it varies a little bit. It's off. So we went back and we wanted to add a drag coefficient. We wanted to do a third model, and in this third model we needed to put in the force drag. So we set up B, which is the coefficient of drag in this equation. That coefficient times the ball's velocity. So the faster the ball goes, the more force drag is going to be pushed back up on the ball. And we'll run it, and what we're going to do is we're going to check for intermediate values. We'll go between this and this value, and we'll see which one is going to give us the result. So this is what we're interested in. So negative 0.9, so we're about halfway there. A 1/100th force drag coefficient in our model. We also went up here and we added, we wanted to write the force net and the force drag. What I predict, and I'm not quite able to do that yet, is to, right here where it says the while is t, if we could make that equal to, and it would only calculate until the force drag equals the force net, then that would give us the time of terminal velocity. If we look at the third model, we can see the predicted motion versus the observed motion. And we can see that the predicted motion may be over-predicted. With the small delta t, it does a lot more calculations. And we can see that it does sort of level out, and which hints at a terminal velocity. For the big question, if the object was thrown, It probably would make a difference in the first couple of frames, but once it gets going, I think the force drag would oppose the weight drag, and the object would pretty much eventually be going at a constant speed.